So far, we have been solving these linear systems in MATLAB just using backslash. So how many people knows what exactly MATLAB do if you do A backslash B? Yes. LU decomposition. Any other? Gauss elimination. Any other answers? Well, you can actually give about 6 to 7 answers that would be correct. So the backslash in MATLAB is actually a more sophisticated thing than most people imagine. So it looks at what A is like and what the right-hand side B is like, and they do different things depending on how the matrix A and B are like. For example, if A is symmetric, it uses completely different algorithms. I mean, even if A is symmetric, it depends on if A is positive definite or non-positive definite, it uses different algorithms. And also, if A is rank deficient, it uses different algorithms. If A is full rank, it uses different algorithms. But anyway, all of these commonality between backslash is it's a class of there are 6 or 7 different algorithms, but all of them are called the direct solution methods. So direct solution methods are anything that is not iterative method. So that's a very not good definition, because iterative methods is actually what we are going to be talking about today. But it actually shares a lot of commonalities with LU decomposition or Gauss elimination. Right, so let's actually review a little bit of what LU decomposition or Gauss elimination does. Actually, they are the same algorithm. Okay, so LU decomposition is just a way to basically it's a matrix way of describing what Gauss elimination does for solving linear equations. So let's just put this in big form, AX equal to B. Okay. So what LU decomposition does is it decomposes A into a lower diagonal matrix we call L times an upper diagonal matrix we call U. So you may ask, how is this always feasible? Well, it is, because you can always start from the very top of the triangle, right? So basically, if you know what's the way of doing matrix multiplication, right? So how do you multiply two matrices? So the way I visualize how you multiply matrices is you decompose the right hand side of the U into different columns, and you decompose the left hand side of the L with different rows, and then you just dot product each row in L with each column in U. That gets you individual entries in the matrix A. So if L is lower diagonal and U is upper diagonal, the very first row of L's decomposition is actually just a single entry, right? And so is the very first column of U is just a single entry. So when you dot product two vectors where one of them is a single entry, you just multiply two numbers. So basically, you will be multiplying two numbers, right, to construct the first row of A and the first column of A. Think about it. So when you multiply the first column of U, which is one number, with any row in L, you are just multiplying that corner of U with the first column of L, right? So basically, this gives you, if you just look at the entries of A, and if you, for example, enforce that all of U's diagonals are ones. I mean, there are two alternatives. Either you enforce L's diagonals are ones, or you enforce U's diagonals to be ones. So if you do one of these enforcement, you will uniquely determine what is the first column of L and the first row of U, just by looking at the corresponding entries of A. Okay? So that works out the first row. That works out the first row of U and the first column of L. And once these are determined, you proceed to the next one, because you already know what is the first row of U and first column of L. This number can be determined from multiplying, I mean this number is 1. This number can be determined by multiplying this column with this row, right? You already know this number and this number, the remaining is over here, right? So if you, all of these algorithms just proceed accordingly. So what's the complexity of this algorithm then? How many operations or how much numbers you have to grab from the memory and manipulate? N cubed, but like you can essentially count, right? So if this is an n by n matrix, this is also an n by n matrix, right? Determine the first row and first column is just n operations. No, just the n operations, right? So, for example, determine the first entry of L is a single operation because I directly take the 1 entry of A and put it in L, right? Because it's multiplied by the 1 in U and just put it there, all right? And in fact, every first column of L can be directly copied from the very first column of A, right? Because the first column of L is multiplied by 1. That gets you the first column of A. All right. Now you know the first column, first entry of L. The first row of U can be determined just by dividing the first row of A by that 1 entry of L. So essentially, you get basically what you get is n operations to determine the first row and column. All right. But then to decide about the second row and column, you actually have to figure out what's the number that is already there, right? So you have to first look at the first column of L and remove that from the second column of A before you can proceed. So basically then the next one is 2 times n minus 1, right? Because I mean you have to remove something and you also have to do something. And the next one is actually 3 times n minus 2 times 4 times n minus sorry for that. Shut off my Slack. Okay. And 4 times n minus 3, etc. up to the very end. All right. So I mean personally, my thinking style is continuous. I mean, if your thinking style is discrete, you may be able to work out this series very quickly. But like the way I think about it is that it's like an integral, right? So it's like an integral, and this is n. You are multiplying. You're basically taking n. You are looking at the integral of n. Times, you're looking at the integral of I times n plus 1 minus I di, right? You're integrating from 0 to n. So essentially, this is going to be about anyway. This is going to be proportional to n cubed, right? All right. Any questions on this? So I'm just approximating a series with the integral. I mean, the discrete series is a summation. The integral is is basically here is I equal to 1, here is I equal to 2, here is I equal to 3, right? So basically I'm writing the series down over here. Okay, so basically this tells you it's an n cubed algorithm to figure out the LU decomposition of the matrix A. And once the LU decomposition is figured out, solving this matrix is actually solving this matrix equation is very easy, because I'm now solving L times U times X equal to B. And the first step is to figure out what is U times X. Okay, L being a lower diagonal matrix, solving it is solving a linear system involving a lower diagonal matrix is called a forward elimination, because the because the first entry of ux is basically the first entry of b divided by the first entry of L, right? And then you figured out the first entry of ux, you substitute it into the second equation, and you get the second entry of ux. You substitute the first two entries of ux into the third equation, you get the third entry of ux. So you figured out ux, right? So let's say ux is equal to y. Then the next step is to solve u times x equal to y. And that process is called a back elimination because u now is an upper diagonal matrix. So you already know y from the forward elimination, then you go backwards. Since u is an upper diagonal matrix, it's very easy to figure out the last entry of x from just a copy from the last entry of y. Since you know the last entry, you plug it into the second last equation, you get the second last entry of x, etc., etc. So basically, you go sweep forward, you sweep backward, you get the solution x. And that process is actually less expensive than the LU decomposition, right? Because the forward elimination involves 1 plus 2 plus 3 plus 4, etc., right? So it's n squared over 2 complexity. The backward elimination is exactly the same, is n squared over 2 complexity. So the elimination is actually proportional to n squared complexity. So that means if you have a large matrix and you factorized it already, if you solve one equation, it doesn't really cost much less than solving a lot of equations with the same matrix but different right-hand sides. Okay, actually, if you try it in MATLAB, it's like solving the same matrix with additional right-hand sides almost comes in for free, right? So if you solve 10 right-hand sides, for example, you can't even measure the difference in the timing if the matrix is large enough. Okay. Primarily, the most of time is spent on factorizing the matrix.